Hi everyone. So in this video, I'm just going to be showcasing how to create a voxel mesh in Unity, and not just a voxel mesh, but also implement some mechanics similar to Minecraft. So let me just show you kind of the results, and then we'll jump into the actual code. So here I'm just going to click initialize a mesh, and it's going to take a second. There we go. Yeah, this vertices list is, as you can see, it has 480,000 total vertices because it's all part of one mesh, and that will typically slow it down. Okay, there we go. So we have I believe this is either 50 by 50 or 100 by 100. I think this one might be 50 by 50. So 2,500 blocks total. And right now I have a depth of 2. This is because sometimes the algorithm that generates it will produce a vertical gap that's more than 2 blocks vertically. This time it didn't though, but that's just kind of a failsafe. And I also have an algorithm that generates trees. Now you'll notice that both the mesh and the mesh and the trees are generated separately. But the mesh, the actual terrain is one mesh, and the trees themselves are one mesh. There we go. But despite them being one mesh, I have the capability actually of editing the meshes individually by removing vertices and even having the ability to place blocks and build something. So again, this is despite the fact that they are all one mesh. Actually, the blocks that I place in this case are their own game objects. It's not because we can't actually add to the mesh, but the problem is when you're interacting with a mesh and you're placing a new object, it has to, when the new object is placed, it will actually have to update the mesh collider of the mesh, and I believe the mesh itself, and a couple of other things, and it ends up being easier from an implementation standpoint easier and faster to just make these your own game object, because the percentage of the ratio of placed game objects to the mesh in terms of the vertex count is so much lower. For example, you can see when I click here, there's a bit of lag every time it's actually going through the mesh, updating it, and updating the mesh collider. You can see it has a mesh collider when I enable gravity on the simple player controller I created, so it actually will disable you from, of course, just floating through the ground, so on. And the same goes for the trees. Yeah, and that's basically it. The day-night cycle is very simple. We just take a directional light and we put a constant rotation on it. So transform.rotate, whatever, 1f, 0, 0. And you can obviously slow that down or speed it up by multiplying it by some sort of speed float. Okay, so another thing is that this actually has a save functionality. So let's pull that up. So the way it works right now is that the mesh is saved inside of this simple text file, and it just has all of the coordinates of the every grass block. Pretty simple. And then we have this other save.txt. This save.txt actually saves the game objects placed by the player. And for example, there's block 2, block 3. So those are actually all of the blocks I placed down. So if I go back to play mode, it's gonna reload that same terrain I generated earlier. So let's take a quick look through the code. So to start this project, I was using Board to Bits games. I was using the tutorial made by Board to Bits, and that one was quite helpful. And insofar as just getting the base cube created with the vertices, faces, and tries. So I'm not going to go too much into that, as I'm just going to link his video, but I'll just do a quick overview. So each one has vector 3 vertices. Each cube has 8 vertices, 0 through 7. And then you generate the face triangles. They're called face triangles, but they're technically squares in a clockwise manner. The north, right, south, left, top, bottom. And then this face vertex function is used to retrieve something later on. The way I'm actually creating the terrain is through let's see, here it is. It's through Perlin noise, where I basically take 3 samples of Perlin noise at different amplitudes. A low frequency amplitude, a mid frequency amplitude, and a high frequency amplitude. And then I add them all together, and this gives us pretty interesting terrain. If you know like anything about waves, such as sine waves, just imagine taking a lower frequency sine wave, such as this. Just take like a low frequency sine wave, and then we can put a higher frequency on top, and then put a higher frequency on top of that. Oh, whoops, I drew this wrong. Something like this. And you kind of have an idea of what's going on here. Of course, it's not going to be just a generic sine wave, because the Perlin noise is random. But it's going to be something a little more interesting. So I'm going to delete the save data so I can regenerate the terrain. And what I'm going to do is I'm just going to change some of the parameters here. So let's make low frequency amplitude 10. And let's do something like this. And then just initialize mesh. Okay, so you can definitely see here we've got something pretty different, where actually in this area it was below a certain threshold, so it got cut off. And you can see in some places where the gap is more than 2 blocks, it's see-through. So that's pretty interesting. So taking a look at what actually goes on here is we use all the Perlin noise to just generate a y value, and we only create a cube if y is greater than negative low frequency amplitude. Why did I do this? Y is greater than... I think this is just to set a floor to the value, so you don't have things going so the bottom floor is flat, and you don't have things going uneven on the bottom side of the mesh. Then we call this makeCube function with our desired coordinates. And we also have our makeTree function. The makeTree function, of course, is a little different from the terrain. And we use this random.range is greater than 48. So there's about a 4% chance on any given tile that a tree will be generated. And the way we do that is we use this data structure here. It might be a bit weird, but this is visually just an upside down tree. These first three rows are just the tree trunk. So this is the first level of the tree trunk, the second level, the third level, and then this is the first leaf level. And here you can go row by row, where the first row has 4, then 5, then 5, then 5, then 3. And then here we start to thin out the foliage, where the first row has 0, the second row has 2, then 3, then 2. And finally, the last row only has, this would make like a kind of like a plus 1, 1, 1, 1, 1. So of course it took me some trial and error because it is kind of weird thinking about it in this sort of manner. But this is kind of like a static data structure which just gets referenced every time we're going to place a tree down. Of course we could put some random values here and random from 0 to 1 and cast it to an int or whatever you want. And then that would give some variance to the trees that are generated. Yeah, that's all I'm going to be going in for now. If you guys want, just leave a comment and I'll go into it much more in depth. If you'd actually like to see how this is done all together. Another part that was fun for me to do was just creating this, where is he? Yeah. This Steve kind of mesh. And the way I actually unwrapped it is similar to what you see in Minecraft texture packs. So I'm actually able to download texture packs and apply it to my mesh. And this was just created in Blender. So I can also have another, I could also create another tutorial for that if you guys want to know how to go about doing that. Let's see. There we go. This is the best skin, probably. Turn off the gizmos here. There. Okay. So, hope you found that interesting. And let me know what you think.